This is a Pokémon card made of Pokémon cards. 32,580 of them to be precise. And it's all done with code. But alright, let's talk about how these were actually made. It all starts with two main ingredients: a reference image, the target we want to recreate, and a database containing, as of now, every single Pokémon card ever released. Now, every single card is a bit tricky to define, since it depends on what we count. Are different language versions separate cards? What about slight reprints? But for reference, the database currently includes 18,454 unique card images. I built this database using a script that systematically downloaded every available card from an API I found online. I'll link all the resources in the description. Along with the images, the dataset also includes metadata, things like the set each card belongs to, release dates, and even the full text of each Pokémon's attacks. This metadata also reveals some interesting insights. For example, these are the most common words in Pokémon attack names. A few trends stand out. There are multiple references to physical attacks, like tackle, punch, and kick, but also elemental moves, energy-based terms, and even references to conditions such as confuse, sleep, and hypnosis. And here's the surprising part. Some of the most common words sound more like they belong in a battlefield, which definitely wasn't something I expected to see in Pokémon. Now, moving back to the process itself, the algorithm begins by overlaying a grid onto the reference image, dividing it into different sections. Each block is going to be swapped out for one Pokémon card. We can choose the size of the grid and have as many blocks as we want. Of course, the more cards we use, the smaller each one gets. At a certain point, they become so tiny that details start to blur when zooming in. To address this, we scale up the entire collage to a higher resolution using standard pixel interpolation techniques. This way, even at a very small size, the cards still look sharp and clear up close. For every block in the grid, the first step is to determine its dominant color, the one that best represents that section of the image. The idea is that we'll later find the Pokémon card that matches this color best. Computers process color as numerical values. In the RGB model, for example, each pixel is a combination of red, green, and blue intensities. So, to summarize all the colors in a block, we need to condense these numbers into a single value. At first I tried taking the average color, basically adding up all the red, green, and blue values and dividing by the number of pixels. But this often produced dull, grayish tones. So I switched to using the median color instead. In math, the median is simply the middle value when you line up all the numbers, and since it's less affected by outliers, it tends to produce a more vibrant and representative color. Once the dominant color of a block is determined, the algorithm searches for the Pokémon card in the database with the closest matching color. We can pre-compute the median color for every card in the database, since these values don't change. But how do we know if a card's color truly resembles the dominant color of a block? At what point do two colors count as close enough? I started with a simple approach. I treated each color as a point in 3D space and measured the Euclidean distance between them. The closer the points, the more similar the colors. While this method works on a basic level, it doesn't fully capture the nuances of how we perceive color. To improve on this, I explored alternative color spaces. You've probably heard of RGB, red, green, blue, and HSB, hue, saturation, brightness, but in this case, the lab color space proved to be much more effective because it's designed to be perceptually uniform. In lab, L stands for lightness, and A and B represent color components that show differences in a way that aligns more closely with how the human eye actually perceives them. Building on this, we can further improve the metric by replacing the Euclidean distance with something more suited to color perception. The CIE delta E 2000 metric is a more sophisticated measure that quantifies the perceptual differences between two colors. Although the math behind it is complex, it essentially tells us how similar two colors look to the human eye. Since collages can sometimes make the original image lose some of its impact, I added a tweak to give more weight to highly saturated colors, keeping things bright and lively. But, of course, the final result also depends on the cards available in the dataset. So, quick break for a fun fact: certain types of cards are far more common than others. Charizard has more than twice as many cards as Blastoise or Venusaur, and middle stage evolutions tend to have fewer versions overall, maybe because they are not as iconic as their base and final forms. Pokémon cards vastly outnumber Trainer and Energy cards, and among them, Water type takes the lead, followed by Grass and Psychic. Evolution stages follow a natural pattern, with Basic being the most common, then Stage 1 and Stage 2. So if we had to pick a single example of the most common type of card, it would probably be Squirtle, a basic Water type Pokémon. So Charmander is the most popular of the 3 original starters, Squirtle is the most representative, and Bulbasaur is, well, my favorite. Alright, back to the algorithm. The final color distance metric is a blend of the CIE delta E 2000 value and a weighted saturation difference, all in the lab color space. There will be one card in the database that scores the best according to this metric when compared to the block's dominant color. However, there will also be others that come very close. To ensure variety and avoid repeating the same cards too often, the algorithm doesn't just settle for the top match. It instead finds multiple candidates for each block. It starts with a quick search using the Euclidean distance method to narrow down the options, then applies the more computationally expensive CIE delta E 2000 metric with the saturation adjustment to the pre-filter candidates. Finally, it selects one card at random from the top candidates, keeping things organic and varied. In some cases, very few cards will meet the criteria, which can lead to repetition once those are exhausted. One possible solution would be to loosen the acceptance threshold, allowing more candidates even if they are not a perfect match. But this could also mean that the algorithm picks suboptimal cards when there are plenty of good ones to choose from. This is evident when looking at how Pokémon cards are distributed along the hue spectrum. Some colors are underrepresented, while others are much more common. Instead, the algorithm uses an adaptive threshold, relaxing the criteria slightly to allow for a bigger difference and re-evaluates the candidates until enough good matches are found. Before placing the selected card into the final collage, we rotate and offset it slightly at random. This breaks up the grid and gives the image a more natural, handcrafted feel. In my opinion, while this creates a more organic result, the perfectly structured grid also has its charm. But now we have options. The algorithm has a variety of settings that allow us to fine-tune the results. For example, we can adjust the size of the grid, tweak how strict the color matching needs to be, and modify factors like rotation and offset ranges, to name a few. With all these options, we can experiment and create collages with varying levels of detail. Depending on the settings, processing time can range from a few minutes to several days. This collage took 2 hours to process on my personal laptop. It's made up of over 32,000 cards with around 11,000 unique ones. The most repeated card was this one, appearing 331 times. By the way, speaking of repeated cards, it's interesting to note that some Pokémon are much more represented than others in the card database. Iconic Pokémon like Pikachu, Charizard, Mewtwo, and Eevee dominate the top spots, while others have only one card. Fun fact, Unknown R actually has fewer cards than the other unknowns. Yeah, I don't know. I'm really happy with how the collage turned out, and I hope this artistic break from my usual game development content was fun for you. If you have any thoughts about the project, feel free to leave them in the comments or join the discussion on Discord. Thanks for watching and see you next time.